we've gone through these. Biochar benefits include nutrient retention, moisture retention in droughts. These are all things that are backed up by loads and loads of scientific literature. Carbon sequestration, which we just talked about. Reducing soil erosion. This is something that I really got to know inside and out when I worked in the soil health lab. So one of the tests that they do in the soil health lab is they put soil underneath a rainfall simulator. And the rainfall simulator is a really cool device that a mentor of mine invented. And he actually gave me one that was like cosmetically imperfect, so they couldn't sell it. But he gave it to me, and I brought it with me to New Zealand. And it's a big plastic or lucite, like hard clear plastic tube this big with big metal or rubber cork in the top and Teflon tubes coming out the bottom, lots of them. And those tubes are exactly the size, and they have exactly this like curl in them, so that when water drips out the bottom of them, they perfectly reproduce raindrops. And we know the exact physics of how much force each raindrop causes when it hits the soil. But why this is so fascinating and important, I think, is it's a way to measure how resistant to water erosion a soil is. And that's an enormous problem in New Zealand because it rains a lot, and a lot of times soil is bare. And a bare soil that's hit with a heavy rain, that's, if there's any slope at all, that's guaranteed erosion. But as most of you are probably aware, like a healthy organic soil tends to stick together and not fall apart and crumble the way a mismanaged conventional soil is. And so we could measure. I mean, I brought this thing with me to New Zealand, so I measure the degree to which a soil falls apart when it's rained on. And even more than that, there are 3 sieves placed underneath the soil sample. So the rainwater hits it and washes off some of that soil down through these sieves. And the sieves are different mesh sizes, and so one of them catches the sand, one catches the silt, and one catches the clay. The one that catches the sand also catches big bits of organic matter and stuff. But it shows it can show you in great detail how resistant to erosion your soil is. And biochar has been shown to make soils more resistant to erosion. And in simplest terms, it can act like the same way compost can act when it's worked into the soil. It can act like a healthy glue that holds the soil particles together. And especially with its fine texture, like the rain can wash it down into everywhere and it can coat all the soil particles. It reduces leaching into groundwater, particularly of nitrogen, which is a huge problem in the Waikato and numerous other places around New Zealand. Reduces or accurate. So it offsets, biochar offsets greenhouse gas emissions in the way that I just described about how plants pull carbon dioxide out of the air, but it also reduces greenhouse gas emissions by when it's applied to soil. Depending on the soil conditions, it's been observed to reduce the most potent greenhouse gas, nitrous oxide emissions, which is 300 times more potent than CO2. And additionally, like I said, if it's fed to cows, it reduces the greenhouse gas emissions from those cows. So I think we're really just starting to scratch the surface of different ways to use the material towards common goals. This is a standard graph showing plant available water capacity. And so this, we've got soil water here in percent organic matter in the soil here. And down here is the level at which plants will permanently wilt. So, and this line is where a saturated soil that's allowed to freely drain, this is how much water is held in that soil. After rain, but after it's drained and it's not standing water. By adding organic matter, including biochar, you can increase the size of this available water pool. You can see that at 1% soil organic matter, the soil can only hold 0.2 cubic meters per cubic meter of soil, cubic meters of water per cubic meter of soil. But if you increase that organic matter up to 6, then you more than double the amount of water that's held in that soil. And that is drought resistance right there. Like the fields that you see that are brown after a drought, and the fields that you see that are still lush and green, assuming one of them doesn't have irrigation and the other doesn't, this is why. And this is something that naturally soils vary. And some have more plant available water capacity than others. But it's also something we can manipulate safely by using natural ingredients like compost and biochar and just encouraging more life in the soil. This is a machine, a specialized soil analytical machine that's used for determining the water holding capacity of the soil. This is just from some work that I did where we were looking at what application rate of biochar produced the most bang for the buck. And so we were looking to identify the perfect application rate for a specific soil. So we applied biochar at all different application rates, and then put it in this machine and generated figures like on the previous slide. And more biochar meant more water holding capacity. It really acts like a sponge for water, and it acts as a sponge for nutrients, like chemically. So it's like physically acts like a sponge, but then also chemically it acts like a sponge because nutrients sit on are adhered to the charcoal surface, and they're held strong enough that water can't wash them off, but they're held loosely enough that plant roots can pull them right off. So biochar adds a time release effect to any kind of fertilizer that's being used. This is a diagram from an old publication of mine, just showing how nutrients run off into surface waters. And biochar in the soil would help filter out those nutrients and retain them before it reaches the surface water. It would also filter them out before the phosphorus or nitrogen leaches into the groundwater and then moves out into the rivers and streams through lateral flow. This is a visual picture or diagram that I made based off of a diagram that my old boss at Cornell published in the journal Nature. And it just shows the global carbon cycle as it always has been, as it always has been over here, where plants are pulling CO2 out of the air into their leaves and respiring oxygen. So they're pulling in CO2, they're putting out oxygen, and it's an even exchange in this system. You see 50% carbon going in, 50% carbon rotting coming out as gases. But when we add pyrolysis, which is the technique for producing biochar, to the system, it reduces the amount of CO2 leaving the system by 20%. Because pyrolysis has some gas emissions, or some emissions, but the emissions from the soil go from 50% down to 5%. When pyrolysis is done in a modern setting, not in a hole in the ground, it's done in these very high-tech kiln-like machines, and they burn what's in there in the absence of oxygen, and there are no gas emissions at all from that type of burning. The only products that come out of the system are contained oils and gases that can be used as a diesel fuel type fuel, and biochar comes out. And pyrolysis has been around for a very long time as a waste management system. You know, it's similar to what some places use for incinerating rubbish, but and the technology sort of fell out of favor until my mentors and their colleagues found a use for the biochar, which used to just be a waste product. But they found out if you produce if you pyrolyze materials that make quality biochar, that's no longer a waste product, and that's another valuable product. In the field trial that I started back in 2007, one of the things that we did, we did all the soil, chemical and biological testing and everything. This is how we tested the greenhouse gas emissions from that field. And greenhouse gas emissions are by the media and by people in general, it's just regarded as something that's like too complex. You can't see it, you can't measure it. All that can be done is like model it with computer models and stuff. And computer models are great, but it's very easy to measure. And like this whole kit for measuring greenhouse gas emissions cost about $5 US. It consists of a plastic bucket with the bottom cut out. So the bottom was cut out of the plastic bucket, so it's just like a plastic tube gently hammered into the soil. It's got a flexible plastic lid that has a ventilation tube coming out of it. And you can kind of see this, or this thing here is a rubber septum, like what's in, like what, when doctors draw medicine out of, with a syringe out of a glass bottle, that's essentially what that is right there. These are vacuum bottles from the analytical lab, so they're just reusable glass bottles that also have a septum in the top. And so we hammered this into the ground and put the lid on, waited 5 minutes, and then stuck the syringe in, took out a certain number of milliliters of gas sample, and put them into the vacuum jars, and put it in with the rest of them to take back for analysis. And it's very easy to do, and it's something that I'm hoping to be able to do here in New Zealand, where greenhouse gas emissions are such a important topic right now. I think a lot of people would be interested to know that it is something they can measure themselves. And this is like the $5 way of doing it. Plus, like the analytical lab charged like $17 for a sample to analyze all greenhouse gases. with all three. But there's also, if you want to spend a few $1,000s, there are devices that can just place out there that are constantly measured. The goal of sustainable agriculture is to meet society's food and textile needs in the present without compromising the ability of future generations to meet their own needs. So we don't have to leave the world or the soil in a worse state than we found it. Our ancestors didn't have the knowledge and the perspective that we have, but we do, and I think we can absolutely leave the world a better place if we so decide. And at the very least, anybody can choose to make their little slice of the world a better place in their lifetime. A sustainable agricultural system includes a lot of things, but 4 elements that I think are very important are eliminating or doing everything possible to reduce fertilizer runoff and leaching. It's just wasteful, and as soon as a fertilizer leaves the farm, it becomes a pollutant. It goes from being an asset to being a pollutant that harms everything downstream. So it just shouldn't be wasted, and we should, I think, more thought should be given to fertilizer strategy. Because there should be a lot of strategy involved with fertilizing, whether it's a garden or whether it's a massive farm. Increasing soil carbon content is critical. Well-rounded plant nutrients, and those things together create a thriving soil ecosystem. Yeah, I'm optimistic because agricultural environmental sustainability is actually taken seriously at present, and it's it's written about in every major publication, and 20 years ago that wasn't the case. It was disrespected, and like organic agriculture, it just wasn't given the respect that it deserved. I think through consumers becoming more aware and the market for organics becoming larger every year the way it has, I think issues around sustainability just started becoming part of everyday people's lives who aren't involved with farming or gardening or anything like that. But everybody's involved with eating. I think we can sustainably produce higher yields of better quality food and improve the soil while we're doing it rather than slowly harm it. So conclusions, or just concluding statements. I think it's really important to check what nutrients your soil lab is testing for. There are good soil labs in New Zealand. I use them a lot in my work. I also send samples to New York, to the Cornell Soil Health Lab, and it's surprisingly affordable, and it's very, very interesting. They do, like I said, nearly 50 tests, and they give you a report that goes through every criteria that they measured and what it all means, and then they synthesize it all in a single graphic that shows on a scale of 1 to 10 where you are, and for every issue that they identify where improvements could be made, they provide helpful suggestions of practically how to do it. I really can't say enough good things about that lab. There isn't another one like it in the world. There's no soil health lab of any kind in New Zealand. There's a soil biology lab, there's some soil chemistry labs, and they do good work for what they do, but it's not the holistic type of test that soil health is, where it takes into account, yeah, the chemical, the physical, and the biological, and after decades of doing it and analyzing the data, like they've just really got it down. I'd love to see that. I would love to open up a franchise lab like that here, just because I think everyone should have access to a lab like that, especially a country that's so economically focused on farming. I think it's just it's required, and it's probably just a matter of time before labs like that exist here, and I hope it happens sooner rather than later. So, biochars, biofertilizers are an excellent way to contribute to the health of your soil and the health of the surrounding environment as well, and to grow bigger, better plants. And I'm happy to answer any questions.